Hey everybody, I'm Silas, and welcome to Psilocybology. Let's expand our mind. This is a series where we talk about the research on psilocybin, the psychedelic prodrug found in magic mushrooms. We'll be breaking down and discussing the scientific literature, one study at a time, from past to present. If you'd like to support the show, please make sure to rate, review, and subscribe to the podcast. Today's episode is on the article titled Effect of Psilocybin, LSD, and Mescaline on Small Involuntary Eye Movements, published in 1966. This study was actually published by one of the same authors from episode 32, a faculty member at Ohio State University named Roland Fisher. I don't often single out particular authors, but I do think it's worth noting that we're going to come across a lot of Roland Fisher's studies as we continue discussing research that took place in the late 60s and 70s, because Roland Fisher was very actively involved in psilocybin research during this time. I believe during my literature search to identify publications that we'd be discussing on this podcast, 31 publications included Roland Fisher as an author. These papers were published between 1965 and 1977. I'd like to point out that this also made Ohio State University one of the leading institutions producing psilocybin research during this time period. Anyway, as you can tell from the study title, this experiment was focused on examining how psychedelics influence involuntary eye movements. There are two key motivations behind this line of research. The first is to find another quantitative parameter that can be used to measure the effect of psychedelics. As an example, one prior measure we've come across is pupillary diameter, which very reliably increases in response to psilocybin, and the amount of pupil dilation appears to parallel the intensity of the trip, with pupils reaching peak dilation during the peak of the psychedelic experience, and returning to normal dilation as the effects of the drug dissipate. The hope by these investigators is to see if patterns of involuntary eye movement could also be used to measure the effects and duration of psilocybin. The second motivation is to see if involuntary eye movements could be used to identify drugs with similar underlying biological mechanisms. The idea being if two drugs create similar changes to involuntary eye movement, they may then also be impacting similar biological processes. Now, in particular, the involuntary eye movements examined in this paper were called nystagmus. These are involuntary eye movements that actually help sustain our vision. To be even more precise, however, the researchers were very specifically interested in one component of nystagmus called saccades. Saccades are quick, simultaneous movements of the eyes that rapidly shift focus from one point to another. Fun fact, saccades are one of the fastest movements produced by the human body. Saccades can occur for a number of reasons, possibly in response to a visual stimulus, in anticipation of a visual stimulus, in response to a memory of a visual stimulus, or they might be attempting to scan the environment. Pretend you're standing on the sidewalk watching cars go by one at a time, and for the sake of example, let's say they're moving from left to right. As you follow one of the cars while it passes by, eventually it leaves your visual field, and your eyes then might jump back to the left and look for a new car that's passing by. That jump would be a saccade. Importantly, the frequency, amplitude, and direction of saccades can be measured, and these are going to be the primary outcomes of this study. Let's move on and talk more about the specifics of the experiment now that we have that background. Personally, I describe this as an exploratory case study. Exploratory because there are no specific hypotheses being tested. I describe it as a case study because the data come from in-depth examinations of 4 participants, and each were exposed to slightly different experimental conditions. When we look at the study procedure, the 4 participants, who were all men, put on a scleral contact lens. A scleral contact lens is a special type of contact lens that fits onto and is supported by the sclera, which is the white portion of the eye. It therefore leaves a space between the contact lens and the cornea. This type of lens has a few different medical uses, but it can also be used to measure eye movements, because scleral lenses can be embedded with mirrors or wire coils. In this study, the lenses were embedded with a small plane mirror that reflected a beam of light to an oscillographic camera. This is called eye-attached tracking, because eye movements are being tracked using something, in this case a mirror, attached to the eye. After putting on the contact lens, which they only placed onto their left eye, the participants were then asked to fixate on the center of a small ring of light located 3 meters in front of their left eye while keeping their right eye closed. A typical experiment consisted of 20 recording sessions, each lasting for about 45 seconds. The first few sessions often took place 30 minutes before drug administration, and the remaining sessions followed drug administration and were spaced out every few minutes up to several hours. Each participant did the experiment at least once after being given psilocybin, but participants also repeated the experiment using different doses of psilocybin, different psychedelics, or with a placebo. The researchers noted that the experiments using the same participant were separated by at least 1 week, so as to avoid the buildup of tolerance or cross-tolerance. The researchers also noted that the participants were experienced in wearing such contact lenses, which I'm sure was an important prerequisite for this line of research. Not to jump too far ahead, but the authors did mention in their discussion that given their findings, future research might want to consider using slightly less sensitive but also less invasive methods that don't require contact use, possibly to more easily get a larger sample. Finally, before getting into the data, I want to talk a bit more about the primary outcomes of this study. As mentioned earlier, the researchers were looking for changes in the frequency, amplitude, and direction of saccades after participants were given psilocybin and occasionally other psychedelics. These changes were compared to baseline patterns of saccadic eye movements. Although it won't be strictly necessary to see and understand the eye movement recordings in order to understand the main takeaway from the study, I'd like to take a moment to describe what the recordings look like. I'll post photos of them on the podcast Instagram, and I'll also include them in the episode transcript for anyone interested, which you can find on the website psilocybology.org. Eye recordings track the movement of the eye using essentially an x-axis that represents time in seconds and a y-axis that represents the position of the eye. What you'll see in these recordings is a squiggly line, and as you follow the line from left to right, you'll see that the line moves up and down over time. I don't see it labeled anywhere in this particular manuscript, but from looking at some other eye recordings during my background research, and assuming there's some form of convention, then when you see the squiggly line go up on the y-axis, this means the eye has shifted focus to the right, and when you see the line go down on the y-axis, this means the eye has shifted focus to the left. In these recordings, what appear as fairly vertical lines are saccades, because these are very rapid jumps from left to right or right to left. Importantly, these jumps can be measured in units called minutes of arc. Now, minutes of arc, also known as an arc minute, is a unit of measure used to quantify very small angles. Importantly, the term minute being used here has nothing to do with the unit of time, but rather comes from the Babylonian number system based on the number 60. 1 minute of arc is simply equal to 1/60th of 1 degree of arc. And degree of arc is just the full formal name for a degree to distinguish it from degrees of temperature, for example. There are 2 key things I want to get across about arc minutes that are necessary to know for this study. The first is that minutes of arc represent the amplitude of eye saccades, and greater values mean that a participant's eye shifted focus by a greater amount. The second thing is that at baseline, saccades had an amplitude of about 5 to 10 minutes of arc. Okay, now let's get into the results. The authors present the data essentially on one participant at a time. So let's start by talking about participant 1. Participant 1 was a 24-year-old male weighing 84 kilograms or 185 pounds. There were two distinguishing features about this participant. The first was that he had been working with these researchers for a year prior to this particular study, and they had obtained a total of 1,020 eye movement records for this individual, so he was very familiar with the study procedure. The second distinguishing feature is that the researchers noted that, for some unexplained reason, the participant was not available for eye movement recordings during the first 90 minutes after taking either 10 milligrams or 13.5 milligrams of psilocybin. Again, they don't explain why, so that data is just entirely missing. They do, however, have data on the first 90 minutes after he was given 15 milligrams of psilocybin. They also have data for the full control experiment, where no drug was administered. I do want to quickly note that for this study, only one participant was given a placebo. For the remaining three, their control experiment was just that no drug was given to them at all, but they did not receive a placebo. I believe part of this is because some participants were familiar with the effects of psychedelics already, and they assumed that the participants would therefore know whether they were given a placebo or not. Anyway, back to participant number 1. During his control condition, saccadic frequencies hovered around 0.4 saccades per second, or about 1 saccade every 2.5 seconds on average. And the amplitude of the saccade was within the normal 5 to 10 arc-minute range. What the researchers found was that there appeared to be a dose-response relationship where the higher the dose of psilocybin administered, the greater the increase in saccade frequency, which appeared simultaneously with an increase in saccade amplitude. Since we don't have the first 90 minutes for two of the experiments, let's compare the saccade frequency 2 hours post-administration for the 3 doses of psilocybin. After the 10 milligram dose, saccade frequency reached about 1.75 saccades per second. After the 13.5 milligram dose, saccade frequency reached about 2.95 saccades per second. And finally, after the 15 milligram dose, saccade frequency reached approximately 3.8 saccades per second 2 hours post-administration. Now, we don't know what the data looked like for the first 90 minutes after participant 1 was given the 2 lower doses of psilocybin. However, the peak frequency after the 15 milligram dose was actually achieved about 75 minutes after administration for participant 1. This peak is reasonably close to the peak pupil dilation that had been recorded in prior studies, which found peaks roughly around 1.5 hours post-administration. Although the paper spends a great amount of time discussing and illustrating the data on saccade frequency, as I mentioned earlier, the authors did note that as frequency increased, there was a parallel increase in saccade amplitude. For example, roughly 2 hours after being given 15 milligrams of psilocybin, the saccades seen in participant 1 ranged in magnitude from approximately 15 to 35 arc minutes, which is much larger than the range of 5 to 10 at baseline. While these findings are already pretty interesting, there was one additional change in the overall pattern of eye movement seen by the researchers, and that was the prevalence of square wave jerks. Square wave jerks are saccades that take the eye off of the point of fixation, in this case the center of the ring of light, followed by a corrective saccade that brings the eye back to the target. Now, square wave jerks reportedly occur in 24 to 60% of healthy adults. The prevalence of square wave jerks is particularly high in children and adolescents, but decreases during adulthood. Although to some degree these particular saccades are normal, they do also occur in greater prevalence among individuals with some degenerative disorders, such as multiple sclerosis or Parkinson's. One thing I read that stuck with me is that while the presence of square wave jerks do not themselves confirm a diagnosis of pathology, because they are found in healthy individuals, the absence of square wave jerks can sometimes rule out certain diagnoses, because some diseases would produce an increase in these saccades. Going back, though, to the data from participant 1, prior to taking psilocybin, the researchers reported that almost 52% of participant 1's saccades could be classified as square wave jerks. After taking psilocybin, this increased to a maximum of 89%. In addition to this increase, they also noted that the increased prevalence lasted longer than the increase in saccade frequency. Although saccade frequency approached normal levels after 3.5 hours, 80% of the saccades seen still formed square wave jerks 3.5 hours post-administration. Essentially, what this seems to show is that after administering psilocybin, participants had a slightly harder time remaining fixated on a given point, and the participants' eyes would more often jump back and forth left to right. Personally, I'd love to know if the increase in frequency of saccades are in response to the hallucinations produced by psilocybin, or if they're contributing to some of the hallucinations produced by psilocybin, particularly given the fact that we know small involuntary eye movements are critical for sustaining our vision. So that was data from participant 1. Let's move on to the second participant. Participant 2 was a 22-year-old male weighing 59 kilograms or 130 pounds, who was given 10 milligrams of psilocybin once, 12.5 milligrams of psilocybin twice, and was also given a placebo pill that looked like the tablets containing psilocybin. Similar to participant 1, the researchers found an increase in saccade frequency, particularly for the two 12.5 milligram doses. Interestingly, with participant 2, they observed that they had a much higher baseline saccade frequency than participant 1. The mean baseline for this participant was 2.33 saccades per second. The peak frequency after 12.5 milligrams of psilocybin, however, reached just above 4 saccades per second, 2 hours post-administration. No changes were seen in saccade frequency in response to the placebo. Now, the researchers don't comment specifically on the change in prevalence of square wave jerks or saccade amplitude for participant 2, but they do make some general statements in their conclusion that we'll bring up in a bit that do make it sound like the responses were largely similar across all the participants after they were given psilocybin. Participant 3 was a 23-year-old male weighing 79.5 kilograms or 175 pounds. So far, participant 1 and participant 2 were only given psilocybin. However, participant 3 was also given LSD and mescaline. Specifically, participant 3 participated in 4 experiments, one using 12.5 milligrams of psilocybin, one using 15 milligrams of psilocybin, one using 123 micrograms of LSD, and one using 450 milligrams of mescaline. Overall, all of the conditions produced an increase in saccade frequency, but there were some interesting differences in the duration of these responses caused by the 3 different psychedelics. For participant 3, both psilocybin and LSD increased saccade frequency to over 4 saccades per second 1 hour post-administration. The key difference between the response to LSD and the response to psilocybin is that after the initial spike, 1 hour after being given psilocybin, saccade frequency drops to between 2 and 2.5 saccades per second by just 2 hours post-administration, and then continues to slowly return to baseline from there. For LSD, however, saccade frequency actually stays pretty elevated and really doesn't start descending rapidly until after 3 hours post-administration, and the largest decrease wasn't actually seen until 4.5 hours post-administration. I think this is about what we might expect, given the longer duration of LSD. It's good to keep in mind, though, that, as always, one difficulty with comparing psychedelics is establishing what are and are not equivalent doses, particularly since it's possible people respond differently to different types of psychedelics. What was sort of unexpected to me was that although there was an increase in saccade frequency seen after participant 3 was given mescaline, the peak increase rose to only about 2.5 saccades per second, a bit over 1 hour post-administration. This increase just seemed a bit lower than what I had anticipated. Despite the smaller increase, however, mescaline did have the longest impact on saccade frequency. Even 6 hours post-administration, saccade frequency was still elevated and doesn't look like it was even starting to descend back to baseline yet. I think that really speaks to the substantially longer duration of mescaline compared to both psilocybin and LSD. Finally, the fourth and final participant was a 22-year-old male weighing 91 kilograms, or about 201 pounds. This participant underwent a control experiment where no drug was given, an experiment using 10, 12.5, and 15 milligrams of psilocybin, as well as an experiment involving 120 micrograms of LSD. In general, the results were largely similar to what we saw with the other participants, including the response to LSD seen with participant 3. I will mention, though, that about 2 hours after participant 4 was given 15 milligrams of psilocybin, his saccade frequency went up to just under 5 saccades per second, which looks like the highest frequency across the experiments conducted, and almost made the peak response to LSD, which reached a bit over 3.5 saccades per second, almost pale in comparison. Now, as I mentioned earlier, they don't specifically discuss the emergence of square wave patterns when discussing the data for each of the participants, but they did state in their conclusion that, quote, these 3 drugs, psilocybin, LSD, and mescaline, produced a characteristic square wave pattern of saccades, which does make me think they found a very similar pattern in participants 2, 3, and 4 as they did with participant 1. So even though that was all the data on psychedelics, the authors actually included one final experiment that they saved for the end of the paper. For this experiment, they went back to using participant 1 and gave him 125 cubic centimeters, equal to about 4.2 ounces, of vodka. In this experiment, they wanted to see how the pattern of eye movement compared to the pattern that they noted after giving participants psychedelics. What they found was that the alcohol produced a very distinct response. Although frequency and amplitude of saccades did still appear to increase a bit relative to baseline, the distinguishing feature is that rather than producing square wave jerks, alcohol appeared to create what was described as a sawtooth pattern, which resembled the pattern seen with gaze-evoked nystagmus. Gaze-evoked nystagmus is produced when individuals have difficulty maintaining fixation. Essentially, their eyes drift off the target slowly, and then eventually a saccade rapidly returns their attention back to the target. When conducting a sobriety test, officers will actually sometimes test for gaze-evoked nystagmus by asking drivers to maintain focus on an object that's usually to the far left or far right of their visual field, and see whether the driver's eyes drift away from looking at the object. In addition to being found after alcohol consumption, it is apparently a common side effect of other central nervous system depressants. To sum everything up, psychedelics appeared to increase the frequency of saccadic movements, the amplitude of the saccades, and increase the overall prevalence of square wave jerks. The key difference between psilocybin, LSD, and mescaline had to do with how long these effects were seen post-administration, and all 3 differed markedly from alcohol, which produced gaze-evoked nystagmus. This sort of speaks to one of the second aims of this paper, namely that it appears that this data support that psilocybin, LSD, and mescaline share some underlying biological mechanism that's separate from how alcohol affects the body, which produced a very different response. And with that, that's all for today's episode. As always, I really hope you enjoyed the show. If you have any questions, feedback, or ideas for the podcast, please let me know. You can find out all the ways to reach me on the website, psilocybology.org, where you can also find the full transcript for each episode if interested. Thank you all for listening, and I'll talk to you next time.